In the year 2000, astronomers were piecing together a violent story. They pointed the new Chandra X Ray Observatory at a galaxy called NGC 6240. This galaxy was a mess. It looked like a train wreck of stars and gas, located about 330 million light-years away. For years, people knew it was the product of two smaller galaxies crashing into each other. But Chandra's X-ray vision cut through the dust and chaos. It saw something remarkable, not one, but two giant glowing cores. These were two supermassive black holes, the engines of the original galaxies. They were separated by a mere 3,000 light-years and were caught in a death spiral. They were destined to merge into one even more massive black hole. This observation was powerful evidence. It supported the idea that galaxies grow by eating each other and their central black holes eventually merge. We could see the before, we could infer the after, but the most violent part of the story, the final collision, was completely invisible. It would happen in a flash of pure gravitational energy, a scream in space-time itself. We had no way to hear it. For that, we needed a new kind of ear. We needed to learn how to listen to the vibrations of the universe. Number 17, Einstein's century-old theory was finally proven right. Albert Einstein himself was unsure if gravitational waves were real. He predicted them in 1916 as a consequence of his theory of general relativity, but he went back and forth on the idea. In one 1936 paper, he and his assistant Nathan Rosen actually concluded that the waves did not exist. The paper was rejected, and a colleague pointed out a mistake in their math, forcing Einstein to reverse his position. For decades, the waves remained a purely theoretical concept, a mathematical ghost. The first confirmed detection of gravitational waves happened on September 14th, 2015, at 9:50:45 Universal Time. The signal lasted less than a quarter of a second. The amount of space-time distortion measured by the LIGO detectors was fantastically small, just 1 part in 10 to the power of 21. This is equivalent to measuring the distance to the nearest star, Proxima Centauri, which is about 4.2 light-years away, with an accuracy smaller than the width of a human hair. The theory of general relativity is our current best description of gravity. It is not just about objects falling down. It is about the fundamental structure of the universe. The theory describes gravity as a curvature of space-time caused by mass and energy. A massive object like the sun creates a dip in space-time, and planets like Earth follow the curves of that dip. This is what we call an orbit. Einstein's equations showed that if massive objects accelerate, they should create ripples in this space-time fabric. These ripples are gravitational waves. They travel outward at the speed of light, carrying energy away from the source. For a long time, this was just an idea on paper. No one had ever seen it happen. The problem was the weakness of gravity. Gravity is by far the weakest of the 4 fundamental forces of nature. The electromagnetic force that holds atoms together is vastly stronger. You can see this yourself. A small refrigerator magnet can hold a piece of paper against the gravitational pull of the entire Earth. Because gravity is so weak, the ripples it creates are almost imperceptible. Only the most extreme, violent events in the cosmos could produce waves strong enough for us to even dream of detecting. We are talking about the collision of black holes, the merging of neutron stars, or the explosion of a massive star in a supernova. These events are the universe's sledgehammers. The quest to find these waves was a long one. It began in the 1960s with a physicist named Joseph Weber at the University of Maryland. He built the first detectors, which were large aluminum cylinders. He claimed to have detected gravitational waves in 1969, but other scientists could not replicate his results. His work was controversial, but it inspired a new generation of physicists to take up the challenge. They knew they needed much more sensitive instruments This led to the idea of using lasers and mirrors, a technique called interferometry. The idea is simple in principle. You split a laser beam and send it down two long, perpendicular tunnels. The beams bounce off mirrors at the end and return to a detector. If the two arms are exactly the same length, the light waves will recombine in a specific way. But if a gravitational wave passes by, it will stretch one arm and squeeze the other for a fleeting moment. This tiny change in length will throw the light waves out of sync. This is the signal. This idea led to the construction of the Laser Interferometer Gravitational Wave Observatory, or LIGO. There are two LIGO detectors in the United States, one in Hanford, Washington, and the other in Livingston, Louisiana. Having two detectors thousands of miles apart is crucial. It helps to rule out local disturbances like earthquakes or trucks driving by. A real gravitational wave from space should be seen at both sites with a slight time delay corresponding to the wave traveling at the speed of light between them. After decades of design, construction, and refinement, LIGO began its advanced observing run in September 2015. It was almost immediately successful. The signal that arrived on September 14, 2015 was codenamed GW. It was perfect. It matched the predictions from Einstein's equations for the merger of two black holes. The signal started as a low-frequency hum, then rose in pitch and volume over a fraction of a second. This is called a chirp. It represents the two black holes spiraling closer and closer, faster and faster, until they finally collide and merge into a single, larger black hole. By analyzing the waveform, scientists could tell a lot about the event. It came from two black holes, one about 36 times the mass of the Sun, and the other about 29 times the mass of the Sun. They merged to form a black hole of about 62 solar masses. What happened to the missing 3 solar masses? It was converted directly into energy in the form of gravitational waves, according to Einstein's most famous equation, E = mc squared. In that brief moment, the merger radiated more energy than all the stars in the observable universe combined. This single event was a profound confirmation of general relativity in a regime where gravity is incredibly strong, something that had never been tested before. Einstein's century-old prediction was no longer a theory, it was an observed fact. The universe had spoken, and we had finally learned how to listen. Number 16, we can now observe black holes directly. A black hole with the mass of the Earth would be about the size of a marble. A black hole with the mass of the Sun would be less than 6 kilometers across. Before 2015, every piece of evidence for the existence of black holes was indirect. We could see stars orbiting what looked like empty space, and from their orbits we could infer the mass of the unseen object. If the mass was large enough and crammed into a small enough space, a black hole was the only explanation. We could see matter being heated to millions of degrees as it was pulled toward a black hole, creating powerful X-ray emissions, but we had never seen the black hole itself or witnessed the direct result of its extreme gravity. Gravitational waves changed that. The signal from GWF 914 was not light. It was not matter. It was a direct vibration of space-time created by the collision of two black holes. For the first time, we were not just watching the effects of black holes on their surroundings. We were observing the black holes themselves as they performed their final violent dance. The signal was a pure manifestation of their gravity. This was a new way of seeing the universe, a new sense. It is like the difference between seeing a drum and hearing it being struck. Light shows us the drum, but the sound tells us about the impact, the vibration, the energy of the event itself. Gravitational waves are the sound of space-time. The waveform of a black hole merger contains an incredible amount of information. The chirp part of the signal, where the frequency and amplitude increase, tells us about the inspiral phase. From the rate of the chirp, we can calculate the masses of the two individual black holes. The more massive the black holes, the lower the frequency of the waves they produce. The final part of the signal is called the ring down. After the two black holes merge, the new, larger black hole is misshapen and unstable. It wobbles like a bell that has just been struck. It settles down into a stable spherical shape by radiating away the last of the merger's energy as gravitational waves. This ringdown is a signature of the new black hole. Its frequency and damping time depend only on the mass and spin of the final black hole. This is a remarkable prediction of general relativity. The theory says that a black hole is a very simple object, described only by its mass, spin, and electric charge. This is often called the no-hair theorem. The ringdown of GL 5914 matched the predictions perfectly. It was the sound of a new black hole being born. Since that first detection, LIGO and its European counterpart, Virgo, have detected dozens of black hole mergers. These observations are building a census of black holes in the universe. We are learning how many there are, what their masses are, and how they are distributed. Before LIGO, we only knew about two types of black holes. There were stellar mass black holes, which are the remnants of massive stars and typically range from a few to a few tens of times the mass of the sun. And there were supermassive black holes, found at the centers of galaxies with masses ranging from millions to billions of times the mass of the sun. There was a huge gap in between. Gravitational wave astronomy is starting to fill in that gap. We are seeing black holes with masses that were unexpected. For example, the final black hole in the GW 5914 event was 62 solar masses. This was larger than any stellar mass black hole previously observed through X-ray studies. Astronomers had thought that stars massive enough to produce such a black hole would blow themselves apart completely, leaving nothing behind. And LIGO's observations are forcing us to rethink how massive stars live and die. We are getting a direct look at the population of black holes that are otherwise invisible. They do not have companion stars to feed on, so they do not produce X-rays. They just move silently through space until they find a partner and merge, and gravitational waves are the only way to find them. This new window on the universe is not just confirming what we already knew. It is showing us things we never expected and forcing us to ask new questions about the most mysterious objects in the cosmos. Number 15, we are witnessing the birth of heavy elements from colliding stars. A single teaspoon of material from a neutron star would weigh approximately 6 billion tons on Earth. These objects are so dense that a neutron star with the mass of our sun would be only about 20 kilometers in diameter, the size of a city. On August 17, 2017, for the first time in history, humanity detected both gravitational waves and light from the same cosmic event. The event, named GW170881, was the collision of two neutron stars. The gravitational wave signal was detected by the LIGO and Virgo observatories and lasted for an unusually long 100 seconds. Just 1.7 seconds after the gravitational waves arrived, NASA's Fermi Gamma Ray Space Telescope detected a short burst of gamma rays from the same region of the sky. This event was a watershed moment for astronomy. It marked the beginning of what is called multi-messenger astronomy. This is the idea of observing the universe using different kinds of signals at the same time. In this case, the signals were gravitational waves and electromagnetic radiation, which includes everything from gamma rays and X-rays to visible light and radio waves. For centuries, all of our knowledge of the universe came from light. Gravitational waves gave us a new sense. Combining them gives us a much more complete picture of cosmic events. The story of GW781 unfolded rapidly. The gravitational wave signal told us the masses of the two objects. They were between 1.1 and 1.6 times the mass of the sun, which is the perfect range for neutron stars. The signal also allowed scientists to pinpoint the location of the merger to a relatively small patch of the sky. Within hours, telescopes all over the world were pointing at that patch. They were looking for the afterglow of the collision, and they found it. A new point of light appeared in a galaxy called NGC 4993, about 130 million light-years away. This was the kilonova, the explosion predicted to occur when two neutron stars merge. For days and weeks, astronomers watched this kilonova evolve. They took spectra of the light, which means they broke it down into its constituent colors. This allows them to identify the chemical elements present in the debris cloud. The spectra revealed the presence of heavy elements like gold, platinum, and uranium. This was a huge discovery. For a long time, the origin of the heaviest elements in the universe was a mystery. We knew that lighter elements like carbon and oxygen are forged in the cores of stars through nuclear fusion. The process stops at iron. Creating elements heavier than iron requires a huge input of energy and a dense environment rich in neutrons. The leading theory was that these elements were created in a process called rapid neutron capture, or the R process. This process was thought to happen in supernova explosions or neutron star mergers. In 178170 provided the first direct evidence that neutron star mergers are a primary site of R process nucleosynthesis. As the two neutron stars collided, some of their incredibly dense neutron-rich material was flung out into space. This material expanded and cooled, and in the process, the neutrons were captured by atomic nuclei, rapidly building up heavy elements. The observations of the kilonova's light, which changed from blue to red over a few days, matched the theoretical models of this process perfectly. The blue light came from lighter R process elements, while the redder light that appeared later was the signature of heavier elements like gold and platinum. The amount of heavy elements produced in this single merger was estimated to be enormous, perhaps as much as several hundred Earth masses of gold and platinum alone. It means that the gold in your jewelry was likely forged in the cataclysmic collision of two dead stars, hundreds of millions or billions of years ago. We are literally wearing the remnants of cosmic violence. This single event solved a long-standing puzzle in astrophysics and showed the power of combining gravitational waves with traditional astronomy. Number 14, we are creating a completely new kind of map of the universe. The first optical telescope, built by Galileo Galilei around 1609, had a magnification of about 20 times. It allowed him to see the moons of Jupiter and the craters on our moon for the first time. The cosmic microwave background, the oldest light in the universe, was discovered by accident in 1965 by two radio astronomers, Arno Penzias and Robert Wilson, who were trying to eliminate a persistent background noise from their antenna. Every map of the universe we have ever made, from ancient star charts to the most detailed images from the Hubble Space Telescope, has been based on light, a form of electromagnetic radiation. Gravitational waves are giving us the tools to create a fundamentally different kind of map. It will not be a map of stars and galaxies as we see them. It will be a map of mass in motion. It will be a map of the universe's most violent and energetic events. It will be a map of the dark side of the cosmos. This is because gravitational waves are not affected by the things that block light. Dust clouds, which obscure our view of the galactic center and other star-forming regions, are completely transparent to gravitational waves. The waves travel through space virtually unimpeded. This means we can hear events that are completely invisible to our telescopes. Every black hole or neutron star merger that LIGO and Virgo detect is a new point on this map. For each event, we can determine its approximate location on the sky and its distance from us. The distance is calculated from the strength of the gravitational wave signal. A stronger signal means the event is closer. The location is determined by a process of triangulation. The signal will arrive at the different detectors, LIGO Hanford, LIGO Livingston, and Virgo, in Italy at slightly different times. By measuring these tiny time delays, we can narrow down the direction the wave came from. The more detectors we have and the more spread out they are across the globe, the better we can pinpoint the source. For future detectors in Japan, Kagra, and India, LIGO India will greatly improve this ability. This new map is already revealing interesting patterns. We are starting to see where these binary mergers are most common. We are building a catalog of black hole and neutron star masses. This catalog is a crucial piece of data for understanding the lives of stars. The masses of the black holes that LIGO has found are often larger than what astronomers expected based on observations in our own galaxy. This might mean that the stars in the distant galaxies where these mergers are happening are different from the stars nearby. Perhaps they have fewer heavy elements which would allow them to grow larger before they collapse. Or perhaps the black holes themselves have grown through previous mergers. This gravitational wave map will also allow us to trace the large-scale structure of the universe in a new way. Well, galaxies are not spread randomly throughout space. They are organized into a vast cosmic web of filaments and voids. By mapping the locations of gravitational wave sources, we can see if they follow this same structure. If a gravitational wave event is followed by a kilonova, as in the case of GW170817, we can identify the host galaxy. This allows us to connect the gravitational wave event to its environment. We can study the properties of the galaxy and learn about the conditions that lead to the formation of these compact binary systems. As we build up a larger and larger catalog of these events, our gravitational wave map will become more detailed. It will be a dynamic map, showing not just where things are, but where the most extreme events are happening. It will be a map of space-time itself, written in the language of gravity. Number 13, we have a new way to measure how fast the universe is expanding. The universe is expanding. We have known this since the work of Edwin Hubble in the 1920s. He observed that distant galaxies are moving away from us, and the farther away they are, the faster they are moving. The rate of this expansion is described by a number called the Hubble constant. Measuring this number precisely has been one of the biggest challenges in cosmology for nearly a century. The problem is that the two main methods for measuring it give slightly different answers. One method uses the cosmic microwave background, the faint afterglow of the Big Bang. This gives a value of about 67.4 kilometers per second per megaparsec. The other method uses standard candles, like certain types of supernovae in the local universe. This method gives a value of about 73.0. A megaparsec is a unit of distance equal to about 3.26 million light years. The discrepancy, known as the Hubble tension, is small, but it is significant. It might be pointing to new physics that we do not yet understand. Gravitational waves offer a completely new and independent way to measure the Hubble constant. These events are what astronomers call standard sirens. The name is an analogy to standard candles. With a standard candle like a Type E, a supernova, we know its intrinsic brightness. By measuring how dim it appears, we can calculate its distance. With a standard siren, like a merging neutron star system, we can calculate its distance directly from the gravitational wave signal itself. The amplitude of the gravitational waves depends on the masses of the objects and their distance from us. By analyzing the waveform, we can figure out the masses. Once we know the masses, the amplitude tells us the distance. This is a very clean measurement. It does not rely on a complicated chain of distance calibrations, which is a potential source of error in the standard candle method. The trick, however, is that to measure the Hubble constant, you need two things: the distance to an object and its redshift, which is a measure of how fast it is moving away from us due to cosmic expansion. The gravitational wave signal gives us the distance, but it does not give us the redshift. For that, we need to find the source of the gravitational waves with a traditional telescope and identify its host galaxy. Once we have the host galaxy, we can measure its redshift by taking a spectrum of its light. This is why multi-messenger events like GW1717 are so important. For that event, we had the distance from the gravitational waves about 130 million light years, and we had the host galaxy NGC 4993, which allowed us to measure the redshift. With just this one event, astronomers were able to make a first estimate of the Hubble constant using a standard siren. The result was about 70 kilometers per second per megaparsec. This value was right in between the values from the other two methods. The uncertainty was still quite large because it was based on only a single data point, but it was a remarkable proof of concept. It showed that the method works. To resolve the Hubble tension, we need to detect many more of these standard sirens. Scientists estimate that we will need to observe around 50 neutron star mergers with identified host galaxies to get a measurement of the Hubble constant that is precise enough to say definitively which of the other two methods, if either, is correct. This is a long-term project. Neutron star mergers are much rarer than black hole mergers, and they produce weaker gravitational wave signals, so we can only see them out to a smaller distance. But as the LIGO and Virgo detectors become more sensitive, and as new detectors come online, the number of standard siren detections will grow. Each new one will add another data point to the calculation, gradually shrinking the error bars. This new technique has the potential to settle one of the biggest debates in modern cosmology. It could confirm our standard model of the universe, or it could provide the first solid evidence that the model is incomplete and that there is something fundamental about the cosmos that we have been missing. Number 12. We can finally probe the extreme matter inside neutron stars. The conditions inside a neutron star are more extreme than anything we can create in a laboratory on Earth. The pressure is immense. The density is staggering. A single sugar cube-sized piece of a neutron star would have the same mass as all of humanity combined. Under these conditions, normal atoms cannot exist. They are crushed into a bizarre soup of subatomic particles, mostly neutrons. But what exactly is this matter like? Is it just a sea of tightly packed neutrons? Or do the neutrons themselves break down into their constituent quarks and gluons, forming a state of matter called a quark-gluon plasma? We do not know the answer. The physics that describes matter at these densities is called the equation of state. There are many different theoretical models for the equation of state of a neutron star, but we have had no way to test them directly. Gravitational waves from merging neutron stars are providing a new tool to study this exotic matter. The key is in the final moments before the two stars collide. As they get very close, the immense gravitational pull of each star starts to deform the other. They are stretched and squeezed. This is similar to how the moon's gravity creates tides on Earth, but on a much more violent scale. The degree to which a neutron star is deformed by these tidal forces depends on its internal structure, which is determined by its equation of state. A stiffer equation of state, where the matter resists compression more strongly, will result in a star that is less easily deformed. A softer equation of state will result in a star that is more easily stretched. This tidal deformation has a measurable effect on the gravitational wave signal. It causes the inspiral to speed up slightly faster than it would for two-point objects like black holes. By carefully analyzing the last few seconds of the chirp from a neutron star merger, scientists can measure this tidal effect. This measurement, called the tidal deformability, puts a constraint on the equation of state. It helps us rule out some of the theoretical models and narrow down the possibilities. The first such measurement came from the GW717 event. The analysis of the signal from that merger favored a softer equation of state. This implies that neutron stars are more compact or smaller in radius for a given mass than some theories had predicted. For a typical neutron star with a mass of 1.4 times that of the Sun, the data from GW178SEN suggests a radius of around 11.9 kilometers with an uncertainty of about 1.4 kilometers. This is a remarkable piece of information. For the first time, we have a measurement that is directly probing the fundamental properties of matter at nuclear density. Another clue comes from what happens after the merger. When two neutron stars collide, the outcome depends on their total mass. If the combined mass is large enough, it will collapse immediately to form a black hole. If it is below a certain threshold, it might form a new, more massive and rapidly spinning neutron star called a hypermassive neutron star. This object would be stable for a short time, perhaps milliseconds or seconds, before it too collapses into a black hole. The gravitational wave signal from this post-merger phase would be very different from the ringdown of a black hole. It would be a high-frequency, more chaotic signal. Detecting this signal would tell us a lot about the equation of state, because the maximum mass a neutron star can support before collapsing depends directly on it. So far, we have not definitively detected a post-merger signal from a hypermassive neutron star, which makes them difficult for the current detectors to see. But as the detectors improve in sensitivity, especially at high frequencies, we hope to be able to see these signals. This will open up another new window into the hearts of neutron stars. By combining information from the tidal deformability during the inspiral and the post-merger signal, we can put very tight constraints on the properties of the densest matter in the universe. This is a perfect example of how gravitational waves are allowing us to do fundamental physics that is impossible by any other means. Number 11. We are testing whether Einstein's theory of gravity is complete. And general relativity has passed every test we have thrown at it for over a century. It correctly predicts the bending of starlight by the sun, the orbit of Mercury, and the timing of pulsars. The detection of gravitational waves from merging black holes and neutron stars was another stunning confirmation of the theory. The observed waveforms match the predictions generated by solving Einstein's equations on supercomputers with incredible precision. But we know that general relativity cannot be the final word on gravity. The theory is incompatible with quantum mechanics, our theory of the very small. At the center of a black hole, or at the moment of the Big Bang, general relativity predicts singularities, points of infinite density, where the laws of physics break down. This is a sign that the theory is incomplete. Physicists have been working for decades on alternative theories of gravity that might solve these problems. Gravitational wave observations provide a new and powerful way to test these alternative theories. Many of these theories predict subtle differences from general relativity, especially in the extreme gravity environment of a black hole merger. For example, some theories predict that gravitational waves should travel at a speed slightly different from the speed of light. The multi-messenger observation of GW 717 put this idea to a stringent test. The gravitational waves and the gamma rays from the neutron star merger arrived at Earth just 1.7 seconds apart after traveling for 130 million years. This means that the speed of gravitational waves is the same as the speed of light to an incredible precision. About 1 part in a quadrillion 10 to the power of 15. This single measurement ruled out a large class of alternative gravity theories that were designed to explain dark energy. Another prediction of some alternative theories is that gravitational waves should have more than the 2 polarizations predicted by general relativity. Polarization refers to the direction in which the wave distorts spacetime. General relativity predicts 2 polarizations called plus and cross. They correspond to stretching and squeezing spacetime in perpendicular directions. Some other theories predict up to 6 different polarizations, including scalar modes that would cause spacetime to expand and contract like a breathing sphere. The network of LIGO and Virgo detectors is sensitive to these other polarizations. By searching for them in the data and not finding them, we can place limits on the theories that predict them. So far, the data is perfectly consistent with general relativity's 2 polarizations. We can also test a fundamental principle of general relativity called the equivalence principle, which states that gravity affects all forms of matter and energy in the same way. Some alternative theories violate this principle. This could lead to a phenomenon called dispersion, where gravitational waves of different frequencies travel at slightly different speeds. This would distort the shape of the chirp signal from a merger. We have looked for this effect in all the detected signals, and we have not seen it. This again confirms that general relativity works as expected, even under the most extreme conditions. The ring-down phase of a black hole merger is another powerful testing ground. As we discussed, the no-hair theorem of general relativity states that a black hole is defined only by its mass and spin. The frequencies of the ring-down waves depend only on these two properties. Alternative theories of gravity can predict different hair, meaning that black holes could have other properties. This would lead to a different set of ring-down frequencies. By measuring the frequencies from the observed ring-downs and comparing them to the predictions of general relativity, we can test the no-hair theorem. So far, all the observations are consistent with the theorem. While all of these tests have so far confirmed Einstein's theory, the search continues. Every new gravitational wave detection is another opportunity to look for a crack in general relativity, a tiny deviation that could point the way to a deeper, more complete theory of gravity. Number 10, we are hunting for primordial black holes as a candidate for dark matter. About 85% of the matter in the universe is dark matter. We know it is there because we can see its gravitational effects. It holds galaxies and clusters of galaxies together. Without it, they would fly apart, but we do not know what it is. It does not emit or absorb light, so we cannot see it directly. The leading candidates for dark matter are hypothetical subatomic particles, but despite decades of searching with sensitive experiments, we have not found any. This has led some scientists to reconsider an older idea that dark matter could be made of primordial black holes. These are black holes that would have formed in the very early universe in the first fraction of a second after the Big Bang. Unlike the black holes we see with LIGO, which form from the collapse of massive stars, primordial black holes could have a wide range of masses, from less than a gram to thousands of times the mass of the sun. If dark matter is made of primordial black holes, they would be all around us, filling the halo of our galaxy. Occasionally, two of them would pass close enough to each other to form a binary system and eventually merge. These mergers would produce gravitational waves that our detectors can see. This provides a new way to search for this form of dark matter. If we could detect a population of black hole mergers with specific characteristics, it could be evidence for primordial black holes. What would those characteristics be? One clue is mass. Primordial black holes could have masses smaller than what is possible from the collapse of a star. The smallest a star remnant black hole can be is about 1.4 solar masses, a limit known as the Chandrasekhar limit. Finding a black hole with a mass less than this would be a smoking gun for a primordial origin. LIGO and Virgo are sensitive to mergers involving black holes down to about 1 solar mass. So far, no such subsolar mass black hole has been detected, which places limits on how much of the dark matter can be made of primordial black holes in this mass range. Another clue is spin. The black holes that LIGO has observed so far have a range of spins. This is expected if they form from the collapse of stars or in dense star clusters where they can interact with each other. Or primordial black holes, on the other hand, are expected to have very little or no spin. If we were to detect a large population of black hole mergers where the individual black holes were all non-spinning, it would be strong evidence for their primordial origin. The rate of mergers is another important piece of the puzzle. If all the dark matter were made of primordial black holes of a certain mass, say 30 solar masses, we can calculate how often they should merge. The number of mergers that LIGO and Virgo have observed already puts tight constraints on this scenario. The observed rate is lower than what would be expected if all the dark matter were made of black holes in this mass range. This has ruled out some of the simplest models where all primordial black holes have the same mass. However, more complex models where the black holes have a range of masses are still possible. The search is ongoing. As the detectors become more sensitive, they will be able to see mergers that are farther away and mergers involving smaller masses. This will allow us to place even tighter constraints on primordial black hole dark matter, where future detectors like the Einstein telescope and Cosmic Explorer will be able to survey a much larger volume of the universe, and LISA, the space-based detector, will be sensitive to mergers of much more massive black holes. This is a search with high stakes. If we were to find evidence for primordial black holes, it would not only solve the mystery of dark matter, but it would also give us a direct probe of the physics of the very early universe, the time when these objects would have been formed. Number 9, we are preparing to listen to the heart of an exploding star. A core collapse supernova is one of the most energetic events in the universe. It happens when a massive star, at least 8 times the mass of our sun, runs out of fuel, and its core can no longer support its own weight and collapses under gravity. The collapse happens in a fraction of a second, crushing the core into an incredibly dense object, either a neutron star or a black hole. The outer layers of the star then come crashing down onto this new compact object, rebound off its hard surface, and create a powerful shock wave that tears the star apart. This is the explosion we see as a supernova. On average, a supernova happens about once every 50 years in a galaxy the size of the Milky Way. The last one we saw in our galaxy with the naked eye was Kepler's supernova in 1604. Our understanding of supernovae is incomplete because the core collapse itself is hidden from our view. It happens deep inside the star, shrouded by thick layers of gas and dust. We can only see the explosion after the shock wave has reached the surface hours or days later. All the crucial physics of the collapse, the bounce, and the explosion mechanism is hidden. Gravitational waves offer a way to peer directly into the heart of a supernova as it happens. The collapse of the core is a violent, non-symmetrical process. Lumps of matter are sloshing around at near the speed of light. This rapidly changing distribution of mass should produce a burst of gravitational waves. The expected gravitational wave signal from a supernova is very different from the clean chirp of a binary merger. It would be a messy, noisy burst lasting for a second or two. The exact waveform would depend on the complex physics of the core collapse. Different models of the explosion mechanism predict different looking signals. For example, if the core is spinning rapidly, it might flatten into a disk and produce a strong characteristic gravitational wave signal. If the explosion is driven by neutrinos, the signal might have a different signature related to the convection and turbulence inside the core. By detecting these gravitational waves and analyzing their waveform, we could distinguish between different models and finally understand how these massive stars die. The challenge is that the gravitational waves from a supernova are expected to be much weaker than those from a binary merger. We would only be able to detect a supernova with the current LIGO and Virgo detectors if it happens in our own Milky Way galaxy or one of its close neighbors like the Magellanic Clouds. Since these events are rare, we might have to wait a while. But when it happens, it will be an incredible scientific opportunity. There is a network of detectors around the world called the Supernova Early Warning Systems News. This network links together neutrino detectors. Neutrinos are tiny, almost massless particles that are produced in enormous quantities in a supernova core. They escape the star almost immediately, about an hour before the light from the explosion. If all the neutrino detectors in SNEWS see a burst of neutrinos at the same time from the same direction, it sends an automatic alert to astronomers all over the world. This is a signal that a supernova has just happened in our galaxy. A gravitational wave signal should arrive at almost the same time as the neutrinos. This would be another amazing multi-messenger event. The combination of gravitational waves, neutrinos, and light from a galactic supernova would provide a wealth of information. The gravitational waves would tell us about the dynamics of the core collapse. The neutrinos would tell us about the nuclear physics and the conditions in the proto-neutron star. The light would tell us about the outer layers of the star and the composition of the ejected material. This combined data would revolutionize our understanding of one of the most important processes in the universe, the process that creates and distributes the heavy elements that make planets and life possible. We are waiting and listening. Number 8, we are searching for the gravitational echo of the Big Bang. The cosmic microwave background CMB is a snapshot of the universe when it was only 380,000 years old. It is the oldest light we can see. Before that time, the universe was so hot and dense that it was an opaque plasma of protons, electrons, and photons. Photons could not travel far without scattering off an electron. When the universe cooled down enough for protons and electrons to combine and form neutral hydrogen atoms, the universe suddenly became transparent. The photons were free to travel through space. The CMB is the light from that moment, stretched out by the expansion of the universe into the microwave part of the spectrum. But what happened before that? What happened in the very first moments after the Big Bang? We cannot see that time with light. The universe was opaque. Gravitational waves, however, could travel freely through this primordial plasma. The very early universe was a chaotic and violent place. It is possible that the processes that happened in the first fraction of a second of the universe's existence could have produced a background of gravitational waves that still fills the universe today. This is called the stochastic gravitational wave background. It would not be a single clear signal from a specific event. It would be a background hiss, a superposition of countless tiny gravitational wave events from the dawn of time. Detecting this background would be like hearing the sound of the Big Bang itself. One of the leading theories about the very early universe is called cosmic inflation. This theory proposes that in the first tiny fraction of a second, the universe underwent a period of incredibly rapid exponential expansion. It grew from a size smaller than an atom to the size of a grapefruit in an instant. This theory solves several major problems in cosmology, but we have no direct evidence for it. Inflation would have violently shaken the fabric of space-time, producing a characteristic spectrum of primordial gravitational waves. Detecting this specific background would be the strongest possible evidence for inflation. There are other potential sources for this background as well. For example, a process called a first-order phase transition in the early universe could have produced gravitational waves. This is like water boiling, where bubbles of the new phase form and expand and collide. If the universe went through such a phase transition, perhaps related to the separation of the fundamental forces, the collisions of these bubbles of new vacuum could have generated a gravitational wave background. Cosmic strings, hypothetical one-dimensional defects in space-time could also contribute to the background as they wiggle and decay. Searching for this background is a major goal of gravitational wave astronomy. It is a very difficult task. The signal is expected to be extremely faint, buried deep in the noise of our detectors. The main strategy is to look for a correlated noise signal between multiple detectors. A real gravitational wave background from the sky would produce a faint correlated rumble in both LIGO detectors and in Virgo. By cross-correlating the data streams from the detectors over a long period of time, we can try to pull this faint signal out of the much louder instrument noise. So far, we have not detected the stochastic background, but with each observing run, the detectors get more sensitive, and the limits we can place on the strength of the background get tighter. This is already starting to rule out some models of the early universe. The search for the primordial background is a long-term game. It might require the next generation of detectors, like the Einstein telescope and cosmic explorer, which will be 10 times more sensitive than the current ones. The ultimate tool for searching for the gravitational waves from inflation might be space-based detectors like LISA, or measurements of the polarization of the cosmic microwave background. The discovery of the stochastic gravitational wave background would be a monumental achievement. It would open a direct window onto the first moments of creation, a time that has been forever hidden from our view. Number 7. We can weigh black holes across billions of light years. Before LIGO, our catalog of stellar mass black holes was small and biased. It was based on X-ray binary systems in our own Milky Way galaxy. In these systems, a black hole is in orbit with a normal star. The black hole pulls material from the star, and this material forms a disk around the black hole. As the material spirals in, it gets incredibly hot and emits X-rays. By studying the orbit of the companion star and the X-ray emissions, we could estimate the mass of the black hole. This method gave us a couple of dozen black hole masses. Most of them were in a narrow range between 5 and 15 times the mass of the Sun. There seemed to be a gap between the most massive neutron stars, about 2 solar masses, and the least massive black holes, about 5 solar masses. Gravitational wave astronomy has completely changed this picture. In just a few years, LIGO and Virgo have detected dozens of black hole mergers. Each detection gives us the masses of the 2 original black holes and the final merged black hole. And we are now building a much larger and more representative census of the black hole population in the universe. We can weigh black holes that are billions of light years away in galaxies we cannot even see with our telescopes. This new census has already brought surprises. The very first detection, GW5914, involved black holes of 29 and 36 solar masses. These were much larger than most of the black holes known from X-ray binaries. Many of the subsequent detections have also involved black holes in this higher mass range from 20 to 50 solar masses. This has forced astronomers to rethink their models of how massive stars evolve and die. It seems that it is possible to form these more massive black holes, perhaps in environments with low concentrations of heavy elements. LIGO has also started to fill in the mass gap between neutron stars and black holes. In 2019, an event named GW84 was detected. It was the merger of a 23 solar mass black hole with a mysterious compact object of about 2.6 solar masses. This smaller object falls squarely in the mass gap. It is more massive than any known neutron star, but it is less massive than any black hole previously found. We do not know what it was. Was it the most massive neutron star ever seen, or the lightest black hole ever seen? We do not have enough information from the gravitational wave signal alone to tell. But the discovery of this object is exciting. It suggests that the mass gap might not be a gap at all, but just a region where these objects are rarer or harder to form. Another surprise is the discovery of intermediate mass black holes. These are the missing link between stellar mass black holes and the supermassive black holes at the centers of galaxies. They are thought to have masses between 100 and 100,000 solar masses. One of the most significant detections so far was GW19. This event was the merger of 2 massive black holes, about 85 and 66 solar masses. They combined to form a new black hole with a mass of about 142 solar masses. This is the first definitive detection of an intermediate mass black hole. The original 85 and 66 solar mass black holes are also puzzling. They are in a mass range where stars are not expected to collapse directly to black holes, a phenomenon called the pair instability mass gap. They may have been formed from the merger of smaller black holes. This suggests a hierarchical model of black hole growth, where smaller black holes merge to form larger ones, which then merge to form even larger ones. By continuing to weigh the black holes across the universe, we are piecing together the story of how they form and grow, from the smallest to the largest. Number 6, we are solving the mystery of short gamma-ray bursts. Gamma-ray bursts, GRBs, are the most powerful explosions in the universe. They are brief but intense flashes of gamma rays that can outshine entire galaxies. They were first discovered by accident in the 1960s by military satellites that were looking for secret nuclear tests. For decades, their origin was a complete mystery. We now know that they come in 2 flavors: long bursts, which last for more than 2 seconds, and short bursts, which last for less than 2 seconds. We have good evidence that long GRBs are caused by the collapse of very massive, rapidly rotating stars, a type of supernova called a hypernova. The origin of short GRBs, however, has been harder to pin down. The leading theory was that they are produced by the merger of 2 compact objects, either 2 neutron stars or a neutron star and a black hole. The problem was that GRBs are notoriously hard to localize on the sky. The gamma-ray telescopes could only narrow down their position to a large patch of sky, making it difficult to find their afterglow at other wavelengths and identify their host galaxy. This made it hard to test the merger theory directly. We needed a way to confirm that a short GRB was happening at the same time and in the same place as a compact object merger. The multi-messenger event, GW7817, provided the smoking gun. As we have discussed, this event was the merger of two neutron stars detected first in gravitational waves by LIGO and Virgo. Just 1.7 seconds later, the Fermi Gamma Ray Space Telescope detected a short GRB named GRB 170817A coming from the same area of the sky. This was the first time a short GRB had been definitively linked to a neutron star merger. It was a beautiful confirmation of the long-held theory. The details of this event were also fascinating. The gamma ray burst was surprisingly faint compared to other short GRBs. The afterglow at X-ray, optical, and radio wavelengths also showed some unusual properties. It took several days to brighten, and it continued to brighten for months. The best explanation for these observations is that we were not looking directly down the barrel of the GRB jet. When two neutron stars merge, the process is thought to launch a narrow, highly energetic jet of material traveling at near the speed of light. This jet produces the gamma rays. If we are aligned with the jet, we see a very bright GRB. In the case of GW17087, it seems we were viewing the event from an angle off-axis. We were seeing the side of the jet, or perhaps a cocoon of material surrounding the jet. This explains why the gamma ray signal was weak and why the afterglow behaved the way it did. This observation has solved the basic mystery of short GRBs, but it has also opened up new questions. It suggests that for every short GRB we see, there may be many more that we miss because their jets are not pointing at us. The gravitational waves can detect these mergers regardless of the orientation of the jet. This means that gravitational wave detectors can act as an early warning system. They can tell us when and where a merger has happened, and we can then point our telescopes there to study the aftermath, even if we do not see a traditional GRB. By combining gravitational wave and electromagnetic observations of these events, we can learn about the physics of jet formation, how the jets interact with their surroundings, and the true rate of these mergers in the universe. We have gone from not knowing what causes short GRBs to being able to study them in unprecedented detail. Number 5. We can search for exotic objects like cosmic strings. General relativity describes the large-scale structure of the universe very well. But there might be strange and exotic objects out there that are also predicted by some theories of physics. One of the most intriguing of these is the cosmic string. These are not the strings of string theory. They are hypothetical one-dimensional defects in the fabric of space-time. They are thought to have formed in the very early universe during a phase transition, similar to the way cracks form in ice as it freezes. They would be incredibly thin, perhaps smaller than a proton, but also incredibly dense and under immense tension. A cosmic string just a kilometer long could have more mass than the Earth. If cosmic strings exist, they would not be static. They would be whipping through space at nearly the speed of light. They could form loops, which would oscillate and radiate energy in the form of gravitational waves. Over time, these loops would shrink and eventually disappear. This process would produce a continuous background of gravitational waves, similar to the one predicted from the early universe, but with a different spectral shape. Searching for this specific type of stochastic background is one way to look for cosmic strings. Another way is to look for sharp bursts of gravitational waves. When a cosmic string has a kink in it, that kink can travel along the string at the speed of light. As it moves, it would beam out a burst of gravitational waves in a specific direction. If such a beam happened to sweep across the Earth, our detectors would see it as a short, sharp signal. We are actively searching for these kinds of unmodeled bursts in the LIGO and Virgo data. A third, and even more exotic possibility, is that a cosmic string could interact with a black hole. If a string were to pass through a black hole, it could be cut. This event would also produce a burst of gravitational waves with a very distinctive waveform. The shape of the signal would be different from anything we expect from a binary merger or a supernova. Finding such a signal would be unambiguous evidence for the existence of a cosmic string. So far, we have not found any evidence for cosmic strings. The searches for the stochastic background and for short bursts have come up empty. This allows us to place limits on how many cosmic strings could be out there. For example, we can say that if they exist, their tension must be below a certain value. As our detectors get more sensitive, these limits will get stronger. We will be able to probe for strings that are lighter and rarer. The search for cosmic strings is a high-risk, high-reward endeavor. They are a very speculative idea. But if we were to find them, it would be a revolutionary discovery. It would be direct evidence of new physics beyond the standard model of particle physics. It would give us a new probe of the very early universe, the time when these structures would have formed. Gravitational wave astronomy gives us a unique tool to hunt for these strange beasts in the cosmic zoo. Number 4, we will be able to peer into the universe's dark ages. After the cosmic microwave background was released, about 380,000 years after the Big Bang, the universe entered a period known as the Dark Ages. There were no stars and no galaxies yet. The universe was filled with a fog of neutral hydrogen and helium gas slowly clumping together under the influence of gravity. This period lasted for several 100 million years. It is dark because there were no sources of light. We cannot study this era with traditional telescopes. The first stars and galaxies eventually ignited, and their ultraviolet light reionized the neutral hydrogen, ending the Dark Ages and making the universe transparent again. But the history of that first stage of structure formation is hidden from us. Gravitational waves could provide a way to illuminate this dark period. One of the most exciting possibilities is the detection of mergers of primordial black holes during this era. If primordial black holes make up some or all of the dark matter, they would have been clumping together along with the gas. They would have formed binary systems and merged, producing gravitational waves. These events would have been happening long before the first stars turned on. Future gravitational wave detectors like the Einstein telescope and Cosmic Explorer will be sensitive enough to see black hole mergers from almost anywhere in the observable universe. This means they will be able to detect mergers that happened during the Dark Ages. The redshift of a gravitational wave signal tells us how much the universe has expanded since the event happened. A higher redshift means the event happened longer ago. The first stars are thought to have formed at a redshift of around 10 to 20. The Dark Ages correspond to even higher redshifts. If we start to detect a population of black hole mergers at these very high redshifts, before the era of the first stars, it would be strong evidence for their primordial origin. It would give us a direct probe of the distribution of dark matter at a time when it was the dominant component of the universe's structure. Another possibility is that the first stars themselves, known as population, the third stars, could be a source of gravitational waves. These stars are thought to have been very different from the stars we see today. They were made of only hydrogen and helium, the pristine material from the Big Bang. Because they lacked heavy elements, they could grow to be enormous, perhaps hundreds of times the mass of the sun. These massive stars would have lived very short, violent lives. Many of them would have been in binary systems. When they died, they would have left behind massive black holes, which would then merge. The gravitational waves from these mergers would be a signature of this first generation of stars. Detecting them would tell us about the masses of these stars and how common binary systems were in the early universe. The Einstein telescope, with its incredible sensitivity, is being designed specifically with this goal in mind. It will be able to listen for the gravitational wave whispers from the end of the Dark Ages, giving us our first direct look at the cosmic dawn. Number 3, we are finally uncovering the missing link black holes. We have known about stellar mass black holes and supermassive black holes for a long time. But the existence of a class in between the intermediate mass black holes, IMBHs, has been hard to prove. These objects, with masses from about 100 to 100,000 times that of the sun, are the missing link in the story of black hole growth. They are important because they are thought to be the seeds from which supermassive black holes grow. One theory is that they form in the centers of dense star clusters where stars can collide and merge, or where stellar mass black holes can sink to the center and combine. These IMBHs could then sink to the center of a galaxy and merge with others to form a supermassive black hole. But finding them has been extremely difficult. They are not as active as the supermassive black holes in galactic centers, so they do not produce as much light. And they are too massive to be formed from a single star. Gravitational wave astronomy is uniquely suited to finding IMBH. The frequency of the gravitational waves produced by a merger depends on the masses of the black holes. And heavier black holes orbit each other more slowly, producing lower frequency waves. Ground-based detectors like LIGO and Virgo are most sensitive to the mergers of stellar mass black holes, which produce waves in the range of tens to hundreds of hertz. Supermassive black hole mergers would produce very low frequency waves in the nanohertz range, which are the target of pulsar timing arrays. Intermediate mass black hole mergers fall in between. The final moments of their merger, the ring down, can sometimes fall into the frequency band of ground-based detectors. The detection of GW192521 was a breakthrough. As mentioned earlier, this event produced a final black hole of 142 solar masses, placing it squarely in the MBH category. It was the first time we had seen the birth of such an object. This single event provided strong evidence that IMBHs not only exist, but that they can be formed through the merger of smaller black holes. It supports the hierarchical growth model. Future observations will be crucial for understanding this population. As the current detectors become more sensitive, they will be able to see more of these massive mergers. The next generation of ground-based detectors will be even better. They will have improved sensitivity at low frequencies, which will allow them to see the in-spiral phase of MBH mergers, not just the final ring down. This will give us much more information about the masses and spins of the individual black holes. The ultimate tool for studying IMBHs will be the space-based detector LISA Laser Interferometer Space Antenna. LISA will consist of 3 spacecraft flying in a triangular formation millions of kilometers apart. It will be sensitive to much lower frequency gravitational waves than ground-based detectors. This is the perfect frequency range for observing the mergers of IMBHs and supermassive black holes. LISA will be able to detect the in-spiral of MBH binaries for years before they merge. This will allow us to measure their properties with incredible precision and to predict exactly when and where they will merge. This could give ground-based detectors an early warning, allowing them to watch the final moments of the merger. LISA will also be able to see stellar mass black holes being captured and consumed by IMBHs, a process called an extreme mass ratio in-spiral. The gravitational waves from these events will map the spacetime around the MBH in exquisite detail, providing a powerful test of general relativity. By opening this new window on the universe, gravitational waves are finally allowing us to find and study the missing link in the black hole family tree. Number 2, we are exploring the fundamental nature of spacetime. At its heart, the discovery of gravitational waves is more than just a new tool for astronomy. It is a confirmation of one of the most profound and bizarre ideas in all of science, that spacetime is a real physical thing. It is not just a passive background on which events unfold. It is a dynamic entity that can be bent, twisted, and made to ripple. We live in an ocean of space-time, and massive, accelerating objects create waves in it, just like a boat creates a wake in water. Before 2015, this was a beautiful mathematical idea. Now, it is an experimental fact. We have built machines that can feel the vibrations of space-time itself as a wave from a distant cosmic cataclysm washes over the Earth. Every gravitational wave detection is a new experiment in fundamental physics. We are probing the nature of space-time in a way that was never possible before. We are learning about its properties. For example, we have confirmed that these waves travel at the speed of light. This is a key prediction of general relativity. We have also seen that the waves behave as the theory predicts. The way they stretch and squeeze space is consistent with the two polarizations of the theory. There is no evidence for extra dimensions or other exotic properties of space-time that some theories predict. But there are still deep questions to answer. What is the quantum nature of space-time? We have a quantum theory of fields for the other forces of nature, but not for gravity. We do not have a theory of quantum gravity. Such a theory would describe gravitons, the hypothetical quantum particles of gravity. Could we ever detect a single graviton? Probably not directly, but a theory of quantum gravity might make other predictions that we can test. For example, it might predict a certain level of space-time foam or quantum fluctuations at the smallest scales. These fluctuations could affect the propagation of gravitational waves over very long distances, causing a blurring or decoherence of the signal. By looking for such effects in the signals from the most distant mergers, we might be able to place limits on some models of quantum gravity. Gravitational waves also allow us to study the most warped regions of space-time in the universe, the event horizons of black holes. The event horizon is the point of no return. It is a one-way membrane in space-time. According to general relativity, anything that crosses it, including light, can never escape. The ring-down signal from a black hole merger is the sound of a newly formed event horizon settling down. By studying the signal, we are directly probing the properties of the event horizon. We are testing the predictions of the no-hair theorem and looking for any signs of new physics at the edge of the abyss. For example, some quantum gravity theories suggest that the event horizon might not be a perfectly smooth surface, but might have some structure. This could lead to echoes in the gravitational wave signal after the main ring-down. People are actively searching for these echoes in the data. Finding them would be a revolution. It would be the first experimental evidence of the quantum nature of black holes and space-time itself. We are just at the beginning of this exploration. We have a new sense, and we are using it to ask the most fundamental questions about the ultimate fabric of reality. Number one, the future is even louder with pulsars and space antennas. The discoveries we have made so far with LIGO and Virgo are just the beginning. They have opened a new window on the universe, but it is a window that is only sensitive to a certain range of gravitational wave frequencies, from about 10 hertz to a few thousand hertz. This is the audible range for gravitational waves from stellar mass objects. To get a complete picture of the gravitational universe, we need to be able to listen to other frequencies as well, from the very low to the very high. The next generation of gravitational wave observatories is being designed to do just that. At the very lowest frequencies in the nanohertz range, we are using the universe itself as a detector. This technique is called a pulsar timing array PTA. Pulsars are a type of rapidly rotating neutron star that emits beams of radio waves from their magnetic poles. As the star spins, these beams sweep across space like a lighthouse. If one of these beams happens to point towards Earth, we see a regular pulse of radio waves. Some pulsars, called millisecond pulsars, are incredibly stable clocks. They are more precise than the best atomic clocks on Earth. A PTA uses a network of these millisecond pulsars spread across our galaxy. The idea is to monitor the arrival times of their pulses with extreme precision. If a very long wavelength gravitational wave passes through our galaxy, it will stretch and squeeze the space-time between us and the pulsars. This will cause the pulses to arrive slightly earlier or later than expected. By looking for a correlated pattern of these timing variations across all the pulsars in the array, we can detect the presence of these nanohertz gravitational waves. This is the frequency range where we expect to see the signal from the mergers of supermassive black holes at the centers of galaxies. In mid-2023, several PTA collaborations around the world announced the first strong evidence for such a low-frequency gravitational wave background, likely produced by the combined hum of countless supermassive black hole binaries across the universe. In the middle of the frequency spectrum, from millihertz to hertz, we need to go to space. This is the domain of the Laser Interferometer Space Antenna, or LISA. LISA will be an interferometer like LIGO, but on a colossal scale. It will consist of 3 spacecraft in a triangular formation, with each side of the triangle being 2.5 million kilometers long. This huge size will make it sensitive to the much longer wavelengths of gravitational waves produced by massive objects. LISA's targets will include the mergers of supermassive black holes, the capture of smaller objects by supermassive black holes emeries, and binary systems of white dwarfs and other compact objects in our own galaxy. LISA will give us a completely different view of the gravitational wave sky. It will be able to hear thousands of sources at once, creating a rich chorus of gravitational sounds. On the ground, we are planning for the next generation of detectors to replace LIGO and Virgo. These include the Einstein telescope in Europe and the Cosmic Explorer in the United States. These third-generation observatories will be much larger and more sensitive than the current ones. The Einstein telescope is planned to be an underground facility with 10-kilometer-long arms in a triangular shape. Cosmic Explorer will have L-shaped arms that are 40 kilometers long. These detectors will be 10 times more sensitive than advanced LIGO. This means they will be able to detect gravitational wave sources 10 times farther away, which corresponds to a volume of the universe that is 1,000 times larger. They will be able to detect every single stellar mass black hole merger in the entire observable universe. They will be able to detect neutron star mergers out to very high redshifts, giving us a precise measurement of the Hubble constant. They will be able to listen for the whispers of supernovae in our galaxy and the echoes of the Big Bang. The future of gravitational wave astronomy is bright. We have only just begun to listen to the soundtrack of the cosmos. Every new detector and every new frequency band will bring new discoveries and new surprises. We are at the dawn of a new era of exploration, one in which we can finally hear the secrets the universe is telling us.